In this tutorial, we'll talk about the different numerical methods in corrosion modeling that we have in COMSOL. In the corrosion module, we have both finite elements and boundary elements. When using finite elements, you discretize the volume so that each element sees only the neighboring elements. This leads to a sparse system matrix, which can be efficiently solved with our solvers. If you use boundary elements that we also have included in the corrosion module, you discretize only the boundaries and the edges using integral equations. This means that each element sees all other elements, and it leads to a dense system matrix. This also gives you essentially less degrees of freedom, usually because you don't have to discretize the volume. But the matrix is dense, and that needs you to use different solver approaches. In COMSOL, we have this current distribution boundary elements interface, which is similar to other current distribution interfaces, but it uses boundary elements instead of finite elements. So in essence, it behaves in the same way as the secondary current distribution interface for finite elements. Sort of also can be utilized to model long edges with internal loss, such as pipelines and such. But it is different since it uses boundary elements, and you also see that you have this domain selection infinite void, which means that you don't need to have a volume to sort of limit your model. You can assume that this volume is infinite. So now I will do a boundary element model. Let's go to COMSOL. So we start first by selecting space dimension, 3D, and then I go to electrochemistry, primary, secondary, current distribution, boundary elements, and I add that. And I want to do a stationary study in this case. So as you can see, the interface looks the same, and we can start by building a block. So I will build a block which is 2 by 2 by 0.1 meters high. So this is a steel surface, and then I want to build a cylinder on top of that, which can be my anode, and that should be positioned like 0.5, 0.5, and then 0.2 along the y-axis, or something like this. And then I also want to show another type of anode, which we call an edge electrode, and you can use that in boundary elements as well, and it's very efficient in boundary elements. And that should be 0.2, 0.2. So here we see a short edge that we put there. These are now my anodes. So then if I go to the current distribution boundary elements interface, I have these two volumes, and the infinite void. And I only want to compute an infinite void in this case, so I remove that from here. And then we can set up the electrode surface. So here I can just select surfaces of the steel like that, and set that to 0 volts. minus 0.6 volts and 10 to the power of minus 2 for exchange current density. And then we do same thing for the anode and set that to 10 to the power of 2 minus 0.05, which is an aluminum anode. And as you can see here, dissolving, depositing species, film resistance, all these things are similar to what you find in the finite element interface as well. And then we can go to edges. Edge electrode. Select this. So that's 0.05. And here we see a different thing that you won't find in the finite element version. That's compensate for tube volume. When you do that, you add a few more degrees of freedom, but you make the current go around. So inside this volume that you have defined with the edge radius here, there will be no current passing through. So that's a useful switch when you model large things such as oil platforms and large pipe with this interface. Then I want to set this to fixed 0 volt and the same 105 and 10 to the power of 2. So yeah, that's it. And now we can mesh it. It automatically meshes the surface like this. And you see it, yeah, 2000 boundary elements. Now we can just compute. And then you get the result. So here you can see that it creates a domain around it where you have extrapolated or you get results from the integration kernels. But you also have the same electrode potential plot that you get when you use the finite element version of it. So this is the way this interface works. And it can be useful in cases where you have complex geometries, large geometries, and particular useful when you want to model jacket structures such as this. So here I have imported jacket structure, and I just want to do a quick assessment of the status of the protection system. And as you can see, I created some selections here, and those are typically based on the import. But now I will just add this physics interface, current distribution boundary elements, and computes in the infinite void. And you set the electrode conductivity here. It's 3 Siemens per meter. And in this case, we just have edges. So edge electrode, set that to 0.4, and so just this I think I'll just use this members interface. So here we have the members. Of course, they are usually of different dimensions, so you need to set that up, but I'm just using 0.4 here. And you need to set it to fixed. And I set it to 10 to the power minus 2, minus 0.6 volts. Then I do the same for the anodes, edge electrode, anodes at 0.1 is okay. edge electrode 2 to set at the fixed potential. So let's minus 0.5, and yeah, then we can go to physics controlled mesh and compute. So as you can see, that computed rather quickly, and yeah, you can have a look at the results here. So for structures like this, it's quite efficient because you don't need to click on all the boundaries, and it also handles the joints in a good manner. So it is quite effective for this kind of models. There's a tutorial in the application libraries for the corrosion module on the cathodic protection, multiple oil platforms, and that shows you how to use this interface. So let's go back to the presentation. I just have a few words on solver considerations. So the default solvers in COMSOL are sort of usually default for a reason. So it's mainly stability and performance that we put. And also it needs to be robust for quite a lot of different applications using these interfaces. So typically for large or corrosion, we use a direct solver. And in this case, we also solve for a level set equation. So it's set up with a direct and a segregated solver approach. If you run out of memory with the direct approach, you might use a multigrid approach. So then you can activate this algebraic multigrid or geometric multigrid solver. This is also a good thing to do on rather large models, because when you have a lot of degrees of freedom, multigrid solver tend to be a bit faster. However, it's less robust than when you have a very poor mesh quality in your model. So there's a few more things that you need to think about when meshing and building the model. But usually it's a quite fast approach to use. One last thing which is important in corrosion modeling is the discretization settings. So when working with sacrificial anodes, the potential drop is large outside the anodes. And it's beneficial to use second-order Lagrange elements to improve accuracy. So this is the default setting for cathodic protection physics interface. But if you just choose a secondary currents interface, you will have linear elements. So then you should go in and change this to a quadratic elements. And this is done by activating the discretization settings in the model builder tree. So I will show how to do that. So let's just go and have a look at this model that we built, and you can see that there's a solver suggestion here, and here it's since it's a boundary element model, it uses different solvers, but there it's a suggested iterative solver. You can just switch to this by enable that, or you can use a direct solver if that works better for you. So this is how the solvers are switched. For the discretization settings, you need to activate this by clicking on this eye, and you need to have this advanced physics options turned on. So here we can go and look at the discretization settings. They are here. So it's quadratic for the potential and linear for the currents in this boundary elements interface. If we open a model with, for example, let's look at this cathodic protection in concrete. We can look at the tertiary current distribution and its discretization nodes. So here we have quadratic for all the different fields that we solve for. But if you go and choose to build a 3D model, let's just do that. 3D model with current distribution secondary. Then you will see that there's a linear discretization for the electrolyte potential. And if you use sacrificial anodes, it's beneficial to use quadratic. It will increase the number of degrees of freedom in your model, but it also increases the accuracy close to the anodes.